Good evening, everybody. I hope you had a wonderful weekend and you did well in your Physics 2 exam. So what I'm going to do here is I'm going to provide an overview lecture of the material that I was going to cover on Thursday. So up to this point, we've covered the fundamentals of digital systems. We've learned some C. You've learned arithmetic logic units. You've learned memory addressing, whether it's cache memory or memory hierarchy. And you have now learned about the data path. So now we are going to understand the concept of performance and design. And so by doing this, what we're going to do is we're going to take this data path that we learned and we're going to break it down into nearly equal tasks. And we're going to do that known as pipelining. So there are 5 basic concepts of this. And in today's lecture, we're going to go into all this and explain how a data path actually works. So the 5 basic concepts of pipelining are dividing the data path into nearly equal tasks to be performed serially and requiring non-overlapping resources. This is going to become very important because we're going to talk about concepts of hazards today. It means we can't have the arithmetic logic unit doing 2 instructions at the same time. We can't have elements being accessed at the same time in terms of pipelining. You can't have memory being accessed, instruction memory. We try to eliminate that. So the second one is insert registers at the task boundaries. Sometimes you also know these as buffers, right? And so registers pass the output data from one task as the input to another task. So you got a buffer in between each stage. And we coordinate this by synchronizing tasks with the clock having a cycle time that just exceeds the time required by the longest task. And they're going to break each instruction down into a fixed number of tasks. And then, we already know in MIPS that number is going to be 5. So that instructions can be executed in a staggered fashion. And so what does this mean? All right, so press pause if you need to write 5.17. All right, now I'm going to scroll down. So here is this idea of a single cycle data path. So I'm going to zoom out a little bit so you can see this whole table. Now, in a load word and store word type instruction, what we're going to be doing is that we need the instruction fetch, we need the decode, we need the execution, we need data memory, and write back. Now, for a single cycle data path, all of them are going to require 8 nanoseconds. All we're doing is during these R-type instructions and branch equivalent, store word, we don't write back. We don't write back during branch. We don't do all this stuff. So for example, jump, you need to do the 2 nanoseconds, right? Instruction decode, you need to do that. We don't do the execution stage, right? All we're doing is writing back, which takes 1 nanosecond. So that becomes the shortest one is 4. However, we have to use the same machine. So in this case, what we're going to be doing is it requires 8 nanoseconds, and that's it. Instead of returning 7 seconds, we add in some time here in the single cycle data path to perform all of this. So as a result, if we do 3 load word instructions, instruction, decode, execution, memory, and write back, and all of them take 8 nanoseconds, the total instruction time it's going to take is 24 nanoseconds. So that is our execution time old. So what we're going to try to do is we're going to use this concept of pipelining to increase the pipelining time. So that means what's going to happen is instruction fetch, and when we're doing instruction decode of the second instruction, we're already fetching the next instruction. And in this lecture, I'm going to show you how the data path is constructed to actually do this. Same thing here, instruction fetch. Now, notice how all of these resources are being used at the same time. If we had a fourth one here, we had instruction fetch, instruction decode. And 4 of them are being used here. So we're going to be running into some issues. However, notice that it significantly cuts down the execution time of the program. That's our benefit, is pipeline. So the improvement execution time old is 24 nanoseconds. The improvement, and that's about 1.7. So this is 5.6. And this is going to be a problem that you will see on the exam. Now, this is a theoretical problem. This is a big thing. And it's really important that you work to understand why this why this problem works out the way that it does. So what we are saying here is assuming n computations. So we just have a program that has n instructions, right? And then this data path has k stages. So in MIPS we have 5. So let's say you had a while loop and it took 10 instructions, of which you took 5 stages in an ideal simple linear pipeline. Now, what I mean by ideal is that we're not going to have any hazards. There's no interrupts. We don't need to insert. We don't have overflow. We don't have any of that. So what we're going to do now is we are going to break everything down into old execution time versus new execution time. So remember that previous example we had 24 and 14? Well, this was the time it took to execute one single cycle instruction was 8 nanoseconds. It had to be the length of the longest one. This value is equal to t of single cycle, right? And that's what TSC is, the clock period. Derive the equation for speed up compared to a non-pipeline and its throughput, where the clock cycle for the single cycle is TSC and pipeline is T of P. So pipeline, what happens is the entire instruction takes, this is T of P, T of P, T of P, T of P. So in that case, remember the previous example, that was 2 nanoseconds, right? So what we end up getting was it took 10 nanoseconds to do each instruction. However, because we're overlapping them, it only took 14 total instructions. So what we're going to have here is we have the total number of stages and time. Right now, in single cycle, each cycle only has 1. So it's no number of instructions times 1 times the time it takes for each cycle to execute. So that's single cycle throughput. So the pipeline throughput is a little more complicated to calculate. And I'm going to tell you how we're going to get this k plus n minus 1 times t of p here. So let us go back to our 5 stages. So we have fetch, decode, execute, memory, write back, fetch, decode, execute, memory, write back, fetch, decode, execute, memory, write back, fetch, decode, execute, memory, write back. So this is 4 instructions, and on an exam you would have a problem where you would actually have to work through 4 different instructions on this. So this takes 1, 2, 3, 4, 5 cycles, right? I'll move this over here so it's a little more clear. So it's 5 cycles for this first instruction, right? So this value is equal to k, because that's the total number of stages in the data path. So that means we have 1 instruction, 2 instructions, 3 instructions, 4 instructions. Right? So we have 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles, 7 cycles, and 8 cycles. So the total time it takes to execute the first 2 instructions is 6, and that's 7, and then that's 8. So we have 5 stages plus 4 instructions is equal to 9. But we want to get to 8. So here's why we're going to subtract 1. And what you're going to see here is it's going to work every time. We have the number of instructions plus the number of stages. So plus 1, right? So that's 5 plus 1. 5 comes from here. 1 comes from this one. But because it's the first instruction, we're going to start here at cycle 1. Think of it as we're going to subtract 1 every time. And that's how we get 5. 6 is equal to 5 plus 2. minus 1. 7 equals 5 plus 3 minus 1. And 4 equals 5 plus 4 minus 1. See how we're allowing for the offset to account for the first instruction. So as a result, as we go through here, the total number of instructions, if we have the first instruction is going to be k, which is the number of stages, plus the number of instructions minus 1. And the time it takes to do that, where both of these are going to be multiplied by each pipeline stage. So it's going to be k plus n minus 1 times t of p. And then the speed up is just the ratio here. And so this throughput is where things get a little tricky, but it's okay. I'm going to help you here with this. So as we get this as the limit as n approaches infinity, first you're going to have, you can break this down, if you recall from calculus, k plus n minus 1 times t of sc over t of p. So as k approaches infinity, n over k plus n minus 1 is going to be essentially infinity. You're not going to have that many stages, 5 or 7 or 8. As this gets into infinity, this gets very close to just n over n, right? So then this just becomes 1, right? 1 as it approaches infinity. So then we have to figure out what TSC over T of P is. So this value is actually pretty easy to figure out, because what we're going to do here is, in the ideal simple linear pipeline, what we're going to do is just going to say, well, this is just T of P times K for T of P, because the whole idea of this throughput is to improve the pipeline of the performance of the pipeline stage over a single cycle data path by breaking it down into K stages. So when you do that, what ends up happening is you get the value of K. I'm going to give you an example. If you had 1,000 instructions times, what we say, T single cycle was 8, right? TP is 2 in the example above, so it'd be 8 over K, 5 plus 1,000 minus 1 times 2, which basically becomes, 1,000 over 1,004. So if we did 1,000,000, be 1,000,000 over 1,004. A billion would be over a billion. See how this basically becomes 1. And then this just becomes the ratio of your speed up over the single cycle over your pipelining. So this is a non-ideal because we figured out the ratio isn't ideal, but still you're getting a speed up of 4 over time. And so how is this actually done? So let me give you a split second to pause. While you're doing that, I'm going to check to see 13 minutes. Okay, good. And so here's how this is actually done. So we have this is a kind of a mock-up of the instruction stages, right? So here you have some sort of result being, branch would be here, and then you have your control signal. So first instruction fetch, we get the result from your PC plus 4 or branch and all that here, right? This goes to the address and puts the instruction out. And then we get to this buffer. So then what ends up happening is that in the second instruction, second stage is going to go there and puts everything on this buffer to wait. In the meantime, we have a second instruction where it goes to the address and it puts the instruction on the buffer. PC plus 4 comes here. So let me show you what I'm talking. So you see, this is the previous cycle. Cycle 3 comes along. We add these results here. We perform this based on put that on the buffer, put that in there, put this result on the buffer, put this result on the buffer, shift left by 2, and put this result on the buffer there. At the same time, we have the second instruction. We get this out here, goes to the control signal, read reg 1, read reg 2, the write register, put the value here, puts on the buffer, and so forth. You can see how that works. So At the same time, we'd have a third instruction where we get the value here, we read the address, we put the buffer on there, like so. So you see how it kind of cascades throughout here? And the whole idea is that this, in fact, this is the reason why you separate instruction memory and data memory, is to eliminate what are known as write after read hazards. And we're going to get into that later today. And so this is where we start adding in buffers. So these little notes here, instruction fetch, instruction decode, execute memory, and write back. So it puts everything here, and you wait, then it goes on to the next stage, and then the first stage puts it on here. Third cycle, red goes here. Second cycle would put everything here, and then blue would put everything here. And so this is the notation where you have fetch. Sorry, what I just had here is fetch, decode, execute, fetch, decode, and that was fetch. Okay, so I want to walk through the entire data path. So here, kind of reiterate this. You get from the multiplexer, you PC plus 4, you get the value, and you put it on the buffer here. Very simple. And then, instruction decode stage, you get stuff from the buffer. It goes to all the read register addresses, sends the value to the control signal. The value PC plus 4 comes across here, and then read data 1, read data 2, and then the sign extend immediate values put here. Execution stage is taking the value from read data 1 off the buffer. This value, sign extend it, then go shift left by 2, put the value here. Sorry. This value comes off of PC plus 4. We add the result, put the result here in between execution stage and memory. The ALU result is put here, and 0 is put there as well. And the read data 2 also comes here. That's the value that's eventually going to go to store word. And then memory stage, sorry, wow, it's a little fuzzy. Memory, give that to the address. It's 0 bit, it's going to come up here. Then we use this result here to go there. Read data comes on the output, and everything we get the value here from read data 2 to go to store word, and everything goes there. And then finally, what ends up happening in the write back stage, and all these diagrams are in chapter 4 of your text. So then you're going to write the result, memory to register here, and then what ends up happening is you go back and you write the data there. So then you can see where we're going to have an issue here, is because there's going to be a point where we're going to be putting a write register address onto this value here. So what we're going to learn is we're actually going to put the write register along here this way. It's going to come along, it's going to come along, it's going to come along, and it's going to go back up here at the same time as the write return comes up there. And so here's a clock diagram. And so this is 5 different instructions. So you got load word, subtraction, add, load word, and add. So you don't, on an exam, you don't have to do it this intricate. What students often do is they'll do fetch, decode, execute, memory, and write back. Fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, write back, and so on. So here what ends up happening is you put the value, you get the instruction, you put this here. Second stage, you put the value in the registers and you get the results out. So here you get 10, and you're going to add this value here. Here, next we go to instruction memory and we get the instruction, put it out there. Stage 3 we're going to put the value of 10 and the offset of 20 on through here, and then add the result and put it on the buffer. Here we're going to take the values of 2 and 3 out of the registers and put them on the buffer. Here we're going to take the instruction and we're going to get the value and set it to the decode stage. Cycle 4, we are going to send this value here. We're going to calculate this and we're going to get the value from the address. Then we're going to take read data 2 from register 2 and read data 3 from register 3, and you're going to subtract them and put that value on the buffer. Here we're going to get the values of 3 and 4 and put them on the buffer in between the registers and the ALU. Load word, you're going to take this instruction here and put it on the buffer. In cycle 5, we're going to write the value we got from 20 and 1 and write that value to register 10. Here, we're going to take this result. It's going to circumvent data memory, which is why there's no blue, and put it on the buffer. Here, we're going to take register 3 and register 4, and we're going to add the result, and then put it on the buffer. Here, we're going to take the values of 1 and 24. You have sign extended value. It's going to go here. And then we're going to get the instruction for add and put it on here. Cycle 6, we're going to take the result of 2 minus 3 off this buffer, and we're going to put it on the register. Here what we're going to do is, because it's an add, we're circumventing 3 and 4, and we're putting it there. Excuse me. Excuse me. We're going to add register 1 and this value here, which is the offset 24, and put that exact address of the array on that buffer. And here we're going to take the values of 5 and 6 and put on these buffers here. In cycle 7, we're going to update the register 12. We are going to get the value from load word. We get the value from data memory. I guess I was wrong about this blue notation. We're going to get the value from data memory. We're going to put this value on the register here. And then we are going to add the read data 1, register 5, read data 2, register 6. And we'll put the result in this buffer. In cycle 8, we're going to take this value here and we're going to load it into register 13, which is there. Here we're going to circumvent the data memory and put the buffer value on the buffer there. And then in cycle 9, we're finally going to update this register here. So normally in class, I ask the students a lot of this question here: what problems could arise? And I let the students wrestle with it for a couple minutes. Now, what ends up happening is, what could arise if I'm updating a register? Let's say this was 3 and 11, right? So what's happening here is I'm getting 2 and 11 here. I'm sorry. Let's say, yeah, this is 3, and let's say this is 11, right? So I'm taking 2 and 11 here, and I'm putting them on the arithmetic logic unit. I've decoded this instruction. I'll be able to break these into different names. So here I'm getting 3, and so I've got the values from 2 and 11, and I'm putting them onto the arithmetic logic unit. At this stage, I'm getting the values that I'm going to get. So here, this register is 3. Here, this register is 4. Now here's the problem. I'm going to calculate the result. So this is a new value of 3. And here we have the old value of 3. And this becomes a big problem. So what we're going to learn about, and this is an example of what's known as a data hazard. And we have to do a lot of work to try to avoid these. Now in single cycle data path, you don't have to worry about it at all because it's just one cycle at a time and you update all the registers before beginning the next instruction. That is not the case in pipelining, and we have to account for it. So give me a split second here. I'm going to check to see how long I've been lecturing. Okay, 25 minutes. All right. So what problems could arise? All right, so ignore that. That's whatever. All right, so this is going to be an exam question 5.18. It's going to be quite a bit. You have to define pipeline hazard and state the 3 types of hazards and give an example. And so I'm going to walk through these and I'm going to describe them and I'll tell you what the examples are. So pipeline hazard is a situation in which the next instruction cannot complete execution one cycle after completion of the present instruction. So the example that I gave you before of this addition and subtraction, we have to wait until the register is updated in that particular instruction because the value of 3 is waiting here. And that is a specific type known as a data hazard, where instruction cannot be completed because the needed data to be generated by another instruction in the pipeline is not available. And so here's an example. So you have 1, 2, and 3, and then what's going to end up happening is you get the values here. You get the values of 2 and 3 on the output. We're going to calculate the register value of 1. However, if we had 2 other instructions, let's say we had subtract, register 4, register 1, register 2, we notice that we have a hazard here because I'm getting the old value out of the register. So I'm using, let's say register 1 was initially 8. And then what ends up happening is you calculate this, and then register 1 new is going to be 4. So what this means is the original value is going to be, that's put here, is going to be 4 because I've calculated the new value. However, the register gets the old value out, so we actually have 8 there. And so this light blue represents all of the potential places where a hazard could place. And basically what this means is I need to somehow get the values back to the arithmetic logic unit before I perform a calculation. And we're going to be going over how to do that later in this section in a concept called data forwarding. So a structural hazard. So here, a structural hazard, 2 instructions cannot exist due to a resource conflict. So here's why I told you at the beginning when I first introduced the data path that we have to separate the instruction memory and data memory. And the reason why is you have to prevent something called a structural hazard. So what ends up happening is this instruction would require memory accesses at memory read at the same time that the 4th instruction requires an instruction fetch. So what I'm doing is if I'm not updating it, I'm updating the local copy of register there, register 10, at the same time that I'm getting this value of 10 in instruction 4. And the problem is that I have to, this is going to be the old version and that's going to be the new version. So I have to wait 1 cycle before I can execute load word. And this will cause a memory resource conflict. Fortunately, we separate instruction memory and data memory in MIPS data path to specifically eliminate this kind of hazard. And then finally, what's known as a control hazard. The instruction to be fetched is not known. And this is going to occur when we have branch equivalent. And here's what I mean by this. So let's say that we have a branch equivalent instruction. So here I am branching to a certain number of instructions. And so I don't know until here what the address is going to be calculated. Furthermore, I don't make this decision where we do the shift left logical here, we bring the value up here, we do all the comparisons. So we don't, in state cycle 4, which is this value instruction here, we don't know whether or not I'm going to branch, or if I branch, I'm going to branch 7 instructions, I'm going to go down here. Otherwise, I'm sorry, down here is 72, right? So if I don't go down there, what ends up happening is I may inadvertently update the register 12, even though the if statement tells me I don't want to do that. So there's a whole method for preventing this, and we're going to learn this as well. So 5.18, you can expect that to be important. Now, you don't have to use these exact three examples. In fact, you can use two instructions. Let me give you an example. So you have add 1, 2, 3, and then I have subtract. As long as the value that's being updated is one of the two values you need to calculate. So if I have 1, 4, and then the result's going to be sent to 6. I'm just pulling numbers out. This is your data hazard. Okay, so in 5.19, we're going to use the concept of data forwarding. We're going to output the resource of an used by an instruction, which output of a resource used by an instruction is forwarded to the input of a resource being used by another instruction. So in that previous example, let's say I have a buffer here, and this is decode execution stage, right? And so I bring the values here, and then they go on to the next cycle to be added. And so first instruction comes in. Here I'm going to add the add 1, 2, 3. Then I'm going to subtract 4, 1, and 2. So this will be instruction 1, and this will be instruction 2 in green. So here in blue, what's going to happen is I'm going to get the value of 2, and 3 here. I'm going to calculate the value that should be on register 1. At the same time, I'm putting the value of 1 and 4. So now, before I execute the next stage, before I put this wrong value of 1, which is here because we've now updated it, what's going to happen is we're going to have another multiplexer compare this result. So what's going to happen is the output of this resource, which is the ALU, is going to be forwarded here, and then we're going to make a decision, and it's going to go, hey, this is the most recent value, and I'm going to put that value here, and then I'll put the other value of 4 here. Oh, damn it. The other value of 4 is going to go here on the ALU. And then we add the correct value of 4. And so we're giving an example 5.6. Show the instances where data forwarding is required in a pipeline data path. So we have these 5 instructions here, and this is also straight from the textbook as an example. So please feel free to refer to the textbook as you study. So here we have these 5 instructions. So you have subtraction, adding, or, add, and subtraction, right? So typically what I end up doing is you have to figure out how many instructions prior to this are going to be used. So the other way I would do this, let's just bring up Notepad, and I'll bring this over here. The only thing I want to do is leave a big white space. So you'd write this out: sub 2, 1, and 3, and you have fetch, decode, execute, memory, and write back. Now, what's going to happen is you got sub 12, 2, and 5. So what's going to end up happening is the result here that's sent out from execution stage of 2 is going to be different than this value we're getting from the value. So you're going to want to circle this one and make this value here. And this is fetch, decode, execute, memory, write back. And what ends up happening is if you do the data forwarding, you would put it to from the output of the arithmetic logic unit from cycle 3. So this becomes cycle 1, 2, 3, 4, 5, and 6 to the input of the ALU at the beginning of cycle 4. So next thing, we're going to do OR 13, 6, and 2. Now, here's the thing. We don't update the registers until cycle 5. So what's going to happen here, I'm going to put this in blue. You have fetch, decode, execute, memory, and write back. So we're now up to 7. So you can do one of two, but see, this output is not being put on this ALU. We're still writing it here from memory to write back here. So what I'm going to do is I'm going to forward from the if you recall from this, we had data memory and the ALU result circumvents it and it's put on the buffer. So what I'm going to do is I'm going to put that result here on the second input of the arithmetic logic unit. So this is another hazard. And then we're going to have this add instruction again, 14, 2, and 2. Well, since it's being updated, but it can't be put on the buffer yet, we're going to forward this. So fetch, decode, execute, memory, write back. Because we can't put it on the buffer yet, we get stopped. We're going to forward this value to the input of the execution stage. And so this is also, these are both data hazards. And since it's been updated, can be put on, the reason why this store word here is specifically to test a specific concept. So we have store word 15, 100, and 2. So we're taking the value from 2 and we're to calculate the base address. In this case, because we have updated the address, we have fetch, decode. So when we do decode, we're moving everything from the registers to put it on the buffer. We actually have the value written into the registers. And that's specifically because we have the known as write then read capability. We have execution, memory, and write back. So it's not a hazard. So we're fine. You can see that is specifically what they were testing. So in 5.8, we're going to go over an example here of how this works. So once again, I'm going to quickly see. Okay, so we have, this will be very similar to an example you see on an exam. So where are my hazards? So we have load word 40 T5 and store the result in register T2. Then we have add, we're going to add temporary register 2 to T8 and store the result in T5. Then we're going to take the results of those values of T2 and T5 and we're going to store the subtraction of those in T3, and then we're going to take the value of T3 and store it in data memory in the location where the base pointer is in T5 and the often offset of 20. So here I've color coded this. So this is part A, assuming no forwarding. So we don't have any forwarding yet. Identify all pipeline hazards between pairs of instructions. So what's going on here is that execution is where I first have the result of 40 plus T5, and I'm storing the result in T2. So I don't have the value until write back. So this is a hazard. That since I don't have it here and I don't have it here for this execution, that means this is also a hazard. And you can see I've notated those in red. The value of T5 is being updated here by the solution of T2 and T8. And because I won't have it here, but I need it, see I need T5 here to perform this execution, right? And this execution. So since they're in the same stage and I haven't been able to write it over to the buffer yet, it is a hazard as well. So these two are notated in light green. And finally, the value of subtraction, T2 and T5, is stored in the register T3, so it's execution, memory, and write back. And since I won't have it here available to the register, I would have to forward it somehow that way. So therefore, this is a hazard. Now, missing this T3 here, is one of the more common student mistakes on exams. Just be aware that that's a hazard because you need to update this value and then you're storing that value from the solution, from the instruction, and storing it into data memory. So, assuming no forwarding, how many inserting stalls, how many do we need? So here's how we calculate this portion, assuming no forwarding. So what we'd have to do is the way you do it is the value that's been updated is able to put it written to the registers and then can put the value onto the arithmetic logic unit in the next instruction. So if you recall the definition of pipeline stages, we specifically stated that what we had to do is you could not complete the instruction one clock cycle after the previous instruction. So normally we'd have fetch, decode, execute, memory, and write back, but we can't do that because we have a hazard between T2 and T5. So to bring back up my notepad here, what we're doing is we have the result stored into your PC. You've got, I'm going to be very execution, memory, and write back, right? So you have fetch, decode, execute, memory, and write back here. And then in the add instruction, I do not have the value of T2 until I've written back to the registers, and then it's available to put on the buffer in the next instruction. I'm putting that value in the ALU. So the trick I always use is I would do execute, I would do fetch decode here. There we go. I would decode and fetch, and then normally it would fetch would start here, so I'd insert 2 stalls. And that's where the operating system is telling it to wait to execute the instruction. So that's why we've inserted 2 stalls here. Same thing. I need this result of T5 before I can execute the next instruction. So I have T5 here, and then I'm going to put the value from the registers into the execution stage. And I do fetch and decode like so. Normally I put it here, so I insert 2 stalls. And then likewise, I need the value of T3 to correctly put the value. So I'm getting T3 from the registers, and then I'm putting it, it's going around the ALU, and then it goes to the data memory where the result of T1E plus T5 is being written. Obviously, read address. So there's your thing. So you add them up, and it becomes 4 total cycles. Now, part C, now we're inserting data forwarding. So let us go through this. You still only have to insert 1 stall, and I'm going to explain to you right now why you're doing that. So I'm going to bring up my notepad here and explain what's going on. So here we have load word, where we have fetch, decode, execution, memory, and write back. Now, if this were add and subtract, what I would do is I would be able to forward this to the next stage, to the next arithmetic logic unit, and not have to worry about any stalls. However, because I'm getting this value out, and then it's going to be first available in the data path, it's going to be taken out of the data memory and put onto the buffer here. So that's where T2 physically appears in the data path, which means I'm going to forward it back to the ALU, which means the next cycle is going to have it available there. And so this is decode and fetch. I would normally start fetch here, so I insert 1 stall. So I have to wait 1 cycle before I can start fetching, decoding, and then executing memory, and then write back. So now, the next instruction is this subtraction, where I have T5 and I need this value. So what's going to happen is T5 is going to be calculated here, and then I can forward it back to the to compare to the values coming from the buffer, so I can put the right one in here. So I can put execution there. So I can do decode and fetch. Well, as it turns out, fetch is right there because this allows us to perform this without inserting any stalls. memory, and write back. And then same thing with T3 here. So I had, right, this should be store word. Okay, so this should be store word. So if we're doing that here with T3, what's actually going on here is I have the value of T3. And so what I can actually do is I can take that value and allow it to be compared here. Right. So this should be store word, T3, 20, and T of 5. So I don't need to insert any stalls there. So the trick is you think about the exact moment. I'm going to write this out for you here. Determine the exact moment when the data is physically available in the data path, and forward it to the execution stage. The ALU operation, per the definition of pipelining, will be executed in the following cycle. And so here you can tell 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles. And so the overall speed up is we initially would require 14 for doing stalls. If we weren't, we would do 5, 10, 15, 20. Then we have it without data forward where we're just inserting stalls, and that knocks us down to 14. So we've knocked it down from 20 to 14. And then we use data forwarding, and that allows us to get down from 20 to 9, which is our performance increase. All right, so how are data forwarding and pipeline stalls achieved in the data path? So I'm going to go over this, and this will be the conclusion of lecture. So if you recall this, we had all of the control signals. Now, we need to be cognizant of where the control signals are being used in each of the stages. So you have execution, data memory, and the write back stages. And so what's going to happen here is all the state instructions come here. You learned about what happens in the control unit, and you put all of them here, right? The application, the execution stage, so you have ALU source, you have your ALU op 0 and ALU op 1, you have your branch over there. So data memory, you got mem read, mem write. Here you're going to have memory to register, and you're going to have your register write, because you want to write the register at the exact stage that you're going to want to use that. So same thing, all the data memory stuff comes here, and all the write back stuff comes here. And so this next topical guide, okay, so this is the actual layout of all of the whole data path. So what we need to do is we have two things. We're going to use a data forwarding unit and a hazard detection unit to indicate where all these values are going to go. So what's going on here is we have our control signal, read register 1, read register 2, and then 15 to 0. And then we have 20 to 16 and 15 to 11. Now, why are we putting these values here? The reason why is we are going to compare our register destination there. And that's what comes from the control units. So that, well, the register write value we're going to do is going to be put here. It's going to be put here. And then it's going to come at the exact cycle that I actually want to execute that. So now I have which register I want to write to. So that's how we put it through the data path. Likewise, register write is going to be coming along here. So if you write write back, write back, write back, and that's what register write's going to do. Likewise, what's happening here is you have your sign extension, just like before, And then you're going to have this value coming in here and circumventing as well. And then you branch, and you can see that's now broken into stages. And so we're going to go over these three. So the hazard detection unit is a unit used to determine if one of the pipeline registered hazard conditions exists in the data path, and inserts a stall if one exists. And so these are the 4 conditions in Topic of Guide Objective 5.22. So I'm going to go back up to the data path here and compare that to this information. So what does this mean? EXM register destination equals IX register source. So what's going to happen here is you have the value between execution coming out here, and RD is the result I'm going to write to it. So this is some R-type instruction. So what I'm going to do is I'm going to bring it here, and it's RS, and I'm going to compare these values. I'm going to have some sort of control signal there. Same thing, I'm going to bring this over here and compare it to RT, which is the value coming out of read data 2. And if these are the same, these 5-bit values, so the value that's going to be here, so if this is T2 and this is T2, that means that the value that I've just updated needs to be used in the next instruction. And so what's going on here is that I have the data memory to write back, so that's 2 instructions ahead, compares with instruction decode execute. So I'm comparing this value and bringing it here, as well as here, and comparing it there. So then if I were to go to red, and so it sends the values here, it detects whether or not I have a hazard. So this is memory to register destination equals register source. So this would be register, so if this was 3 instructions, this would be register instruction 1. These are all instruction 1. And this would be instruction 2, which would be the next instruction, and then instruction 3. There. Okay, and then the data forwarding unit is a control unit which takes inputs from the control signals at each stage and forwards the values to the inputs of the arithmetic logic unit. All right. And then we'll end at 5.24. And so 5.24 is the data hazard detection unit here. This is the control signals. So forward A is 0, 0. That means it's the instruction fetch, instruction decode. That means we have no hazard, and that's the correct value. That means the second instruction has a data hazard, this data forwarding unit, and tells me I need the RS value. And then 0, 1 is memory and write back. So that means I need the RS value. That RD value is the same as RS value in the second instruction. Forward B, so you have RS, so you have your RS or RT, whatever value. So this is RT actually, because it's forward B. And then RD is the same thing as RT. So we have a hazard here, so we need to use this one. And then likewise, this is the most recent version of the instruction, and it's there. All right, so on that note, I know it's an hour and 15 minutes, but I usually try to allocate approximately 20 minutes or so to questions and explaining concepts in a little more detail. So I'm going to stop here, and I'm going to conclude the lecture and start lecture by asking questions about this.